Hey guys, so today we're going to talk about the wave description or the wave nature of light. So prior to the early 1900s, it was always believed that light was a wave. So we're going to describe some of the characteristics of light and some of the characteristics of waves today, and at the end of the video, hopefully make a very good argument for light being a wave. So the majority of the waves that we'll talk about in chemistry are in the form of electromagnetic radiation. So all electromagnetic radiation is an energy that has wave-like behavior while traveling through space. So if you look at the word electromagnetic, you could probably guess that electromagnetic radiation arises from some combination of magnetic and electric fields. So let's look at the different forms of electromagnetic radiation, or the different forms of electromagnetic waves that we'll deal with. So if we call it the electromagnetic spectrum, that means there is a wide range of these waves that we can examine. So we start off, and this spectrum can be listed in the direction I write it or backwards. It doesn't really matter how you write it. So the first type of wave that we will write is radio waves. So radio waves are radio electromagnetic radiation. We call them radio waves for the most part. Then we have microwaves. Okay. Then we have infrared. Then we have visible light. I'll just write it as visible. So these are the lights that humans can detect. So the colors of the rainbow, you would imagine. So then we have, I'll abbreviate it UV, ultraviolet radiation. Then we have X-ray radiation. And I'll squeeze it in here, we have gamma radiation. Okay. So the way this is written, you could probably guess just on what you know about some of these types of waves, that this end of the spectrum is the lowest in energy. And that this end of the spectrum is the highest energy. Okay, so before we discuss this spectrum anymore, let's come down and let's look at an individual wave, and let's talk about some vocabulary that we'll use to describe these waves. So I'm just going to draw one wave. And sorry, that's not good. That should be fairly symmetric. And this is a single transverse wave is how we could describe this. So an electromagnetic wave actually has, it would be two waves similar to this traveling opposite to each other. So you would have an an electric field and a magnetic field traveling in opposite directions. But don't worry about that for right now. Let's just consider this single wave for now. So a couple of terms that we'll use. The first term is amplitude. Okay. And the amplitude is really the height of a wave, is another way to say it. Okay. So a couple of terms that we'll use to describe the amplitude of a wave. You'll have the crest, which is the highest point of a wave, and the trough, which is the lowest point of a wave. So one important thing about amplitude, it is directly proportional to energy. Okay. So the greater the amplitude, the greater the energy of a wave. So another term that we'll use to describe waves is wavelength. Okay. So the wavelength, I'll abbreviate that, WL, is the length of one complete wave. So in your notes, it uses a little bit different terminology. In your notes, we describe the wavelength as being the distance between two consecutive and corresponding points on a wave. Okay, so the term distance between consecutive and corresponding is a little bit tricky. So it's easier to say it's the length of one complete wave. So a complete wave must include one crest and one trough. So if you think about the wavelength, we could measure from this point to this point. Okay? That could be the consecutive and corresponding points on the wave. So you can measure crest to crest, or if I had drawn the rest of the wave, you can measure trough to trough, or you could pick some point in between, and as long as you choose the exact same point on the next wave, you'll get the same length. But for the sake of this discussion, let's just consider the distance between the crests of consecutive waves. That makes it easier to look at. So an important thing about wavelength is inversely proportional to energy. So that means the greater the distance between two crests, so the longer the wave, or the longer the wavelength, the lower in energy the wave actually is. So now let's come back up here, now that we have some terminology, particularly wavelength to use, let's look at the spectrum. Okay? So if we know that the radio wave end is the lowest in energy, I know that this end of the spectrum is going to have the longest wavelength. And I'll abbreviate that WL. Okay? So I can say the greater wavelength. So this end is going to have, I'll just say shortest wavelength. Okay? And again, I could write this spectrum as the exact opposite, so we can't make the assumption as you move right across the spectrum you gain energy or you decrease wavelength. That's not always true. The exact opposite could be true depending on how you write the spectrum there. So a couple of other notes about wavelength. Wavelength is a distance, so we could measure that in any of our units that correspond to distance. So we could measure it in kilometers, we can measure it in meters, we can measure it in nanometers. So obviously that depends on what part of the spectrum we're dealing with. If we're dealing with this part of the spectrum down here, the radio wave spectrum, we will probably measure wavelength in meters or kilometers. Okay? So they have very, very long waves. The section of the spectrum that we're most familiar with is the visible light spectrum. Okay, we typically measure the visible light area of the spectrum in nanometers. So obviously the visible light spectrum is red, orange, yellow, blue, green, indigo, violet, and it shouldn't be hard to figure out, which way the spectrum goes. Infrared should connect with the red, and ultraviolet should connect with violet. So if I were to write out the visible spectrum, red, orange, yellow, blue, green, indigo, violet, okay, I now see that I could describe each of the colors of light based on its wavelength. So I could give you a certain wavelength of visible light, and you could go to a table and tell me exactly what color that light was. Okay, so another term that we'll use to describe waves is frequency. So frequency is exactly what you think it would be. It is how frequent the wave occurs. So how often do we have a crest and a crest, or how often do we see two troughs together? So frequency we measure in a unit called hertz. And that's abbreviated Hz. So all hertz corresponds to is an inverse second. Okay, so that is 1 over second. So you could read that as per second. So frequency can be thought of as waves per second. It's another way to say that. So if you think about wavelength and frequency, if a wave is very long, the crests are far apart, do you think the wave would occur more frequently or less frequently? Yeah, hopefully you said less frequently. So wavelength and frequency are inversely proportional here. So the longer a wave, the less frequent the wave occurs. So a couple of the symbols we use for wavelength, we'll use the Greek letter lambda, and for frequency, we'll write it as a V. It's the Greek letter nu there, I believe, but we write it and type it as a V for the most part. So I can come back up here and also label this spectrum. If it has the longest wavelength, it has the lowest frequency. So if it has the lowest wavelength or the highest energy, it has the greatest frequency. Okay. So now just with what I have here, you could compare two types of electromagnetic radiation. Microwaves that you use in your home quite often, you can probably guess where, versus X-rays. If you break a bone, what the doctor is going to use to look at your bones. You could compare them in energy versus wavelength here. So if I ask you which color of light, red or green, is higher in energy, you should be able to tell me that at this point. You should be able to say, okay, green is closer to gamma rays in the spectrum. I know gamma rays have the highest energy, they have the greatest frequency, so I know that green light is higher in energy than red light. So this is one thing that leads us to believe that light is a wave. It has characteristics such as wavelength and frequency that I can use to compare each other. So I can say blue light is lower in energy than green light because it has a longer wavelength, for example. So that is one piece of evidence that leads us to believe that light is in fact a wave here. So one thing about the electromagnetic spectrum before I continue is what we call a continuous spectrum. Okay? So it's not that I have this nice little area of wavelength where it's radio waves. We skip some, then it's microwaves, and we skip some, then it's infrared. So there is no gaps between these types of radiation. You continue smoothly from one to the other. There is no space in between. Okay, so another piece of evidence that would lead us to believe that light is in fact a wave is the presence of constructive and destructive interference. So I'll label constructive interference, I'll just say CI, okay, can make light appear to be brighter. So what constructive interference looks like, all it is the combining of waves. So if I have this wave, and this is a very simplified example obviously, and I have this wave, and they get combined together, okay, I just get a wave, okay, with a greater intensity there. Okay, so I can see a more intense light. Then I have destructive interference, okay. It can actually cause light to disappear here. So it is the opposite of constructive interference. Constructive interference combines waves in a positive way. Destructive interference combines waves in a negative way. So if I had a wave like this plus a wave like this, okay, they could potentially cancel out to give no wave. Okay, and light does this. I'll post a video showing some experiments where light waves actually cancel each other out here or combine constructively. So this is another piece of evidence that leads us to believe that light is in fact a wave here. It has this characteristic of constructive and destructive interference of waves. And so another thing we want to consider is what happens when you pass white light through a prism. So when you pass white light through a prism, it is bent twice. Sorry about that, my doorbell rang. So what I think I was saying was when white light travels through a prism, the beam of white light is bent twice, and what you see come out is a rainbow. Okay, but it's a rainbow in a continuous spectrum. So again, what that continuous spectrum means is I don't see one color here, some space, one color here, some space, and one color here. I see the continuous spectrum of the rainbow. Okay, so one color gradually fades into another. So the same thing was true about the electromagnetic radiation. Okay, so one form of energy or radiation gradually shifts into another. So these are just kind of names that humans have placed on each of these categories of electromagnetic radiation. There is nothing inherently special about the visible spectrum that allows us to see it. What is special about that is that the human eye system actually picks up those specific wavelengths of light. So there's nothing inherently special about that light other than that humans can pick it up. Okay, other wavelengths of light could potentially be seen by other creatures. And so the fact that we see this continuous spectrum is one of the best pieces of evidence that light is in fact a wave. It can be separated out into its constituent components. So now, after looking at all this information, we see that light has a wavelength and it has a frequency. Okay, so if it has a wavelength and a frequency, those are properties of waves, so it's a pretty good assumption to make that light is in fact a wave. So this was the prevailing theory for many, many years, and it's still believed to be true. It's still agreed upon that light is a wave, but now we know it is just not completely correct to call light only a wave. So the fact that light is a wave allows us to do some interesting calculations. So it turns out that all electromagnetic waves travel at the same speed when inside a vacuum. So when I say inside a vacuum, that means there are no particles it's having to travel through, so nothing to slow it down. So all electromagnetic waves travel at the same speed, and we call that c. Lowercase c is our symbol here, and we more commonly refer to that as the speed of light. Okay, so that makes sense. The speed of light is how fast a light wave travels in a vacuum. It just so happens that the speed of light is also how fast an X-ray travels, or how fast a radio wave travels, or how fast a gamma wave travels. Excuse me, gamma wave. Having trouble talking this morning. So we know the numerical value for that. So we know the speed of light is 3.0 times 10 to the 8th meters per second. Okay, so obviously we know a much better number for that. We could write that out 2.998 and then a lot more decimals times 10 to the 8 meters per second. But for the sake of this class, we will round that to 3.0 times 10 to the 8th meters per second. So our formula for wavelength, for the speed of light, is the speed of light equals wavelength times frequency. Okay? So let's just plug in the units here for each of these symbols and look at what's going on. So the speed of light is in meters per second. Wavelength is length, so we can measure that in kilometers, meters, nanometers. So let's just plug in meters there. We remember that frequency is measured in hertz. Okay, or I can measure it in millihertz or megahertz or kilohertz. I could add the prefixes on that just like anything else. But I know that a hertz is, I guess I would hurt, I don't know what the singular form of that is equal to an inverse second, so 1 over a second. So I see this formula holds up. A meter times 1 over a second gives me a meter per second. So now I have a way to convert from frequency to wavelength, because I know c is always going to be the same. So c is a constant. So if I know either wavelength or frequency, then I can use this formula to convert back and forth from one to the other. It is important to note, though, the units for the speed of light and frequency must be the same. So typically we leave c in terms of meters per second. So we always need to change our units for wavelength to meters. So visible light, which is what we deal with quite a bit, has a wavelength in the range of several hundred nanometers, so nm. So we'll have to go back and use our dimensional analysis to convert from nanometers to meters in the majority of these problems we deal with. Okay, so if you look at the first example in your notes, and before I do this, let me back up and say one thing I might not have mentioned. So I think I mentioned it earlier. So we define colors by their wavelength and frequency. Okay, so every color has a corresponding wavelength and therefore a corresponding frequency. So that is a way that we can define colors. Okay, so blue light, I can't really define that. If I'm if I were colorblind, for example, it would be very, very difficult for you to describe to me in terms that I could understand what blue light looks like. So we can numerically describe light by saying its specific wavelength value or its specific frequency value. Okay. So now let's look at some of the example calculations in the notes. So the first one asks you to calculate the wavelength of yellow light emitted by a sodium lamp if the frequency of the radiation is 5.10 times 10 to the 14th waves per second. So here it says waves per second. So another way to say waves per second is hertz. So I could say that frequency equals 5.10 times 10 to the 14th hertz is another way to write that particular problem out. Okay, so at this point I really only have one formula that I've used to deal with light, so this calculation should be fairly easy. So I have the speed of light equals wavelength times frequency. So before I start, I go ahead and do my algebra and solve for wavelength, so lambda. So wavelength equals, so when you do that algebra real quick, what do you get? Yep, hopefully you said the speed of light divided by frequency there. So now I can go ahead and plug in. So wavelength equals the speed of light is 3.0 times 10 to the 8th meters per second. And yes, you have to write in the units here. If you don't write in the units, you won't get credit, because writing in the units will help you catch a lot of simple mistakes that you might make. Okay, so I know here that the frequency is 5.10 times 10 to the 14th. I could write it as hertz, but writing it as inverse seconds would make it much easier to see. So then the seconds would flip to the top, the numerator of the numerator up here. So I would cancel those out and I'd be left with meters. Is meters a valid unit for wavelength? Yes, it is. So I know I'm at least on the right track if I end up with valid units. So go ahead and type that in the calculator and see what you get. Okay, so hopefully when you type it in, you get 5.8824 times 10 to the negative 7th meters. So I go back to the original problem. I see that I have 3 significant digits. Remember, for constants, I do not consider significant digits here. So I round this off to 5.88 times 10 to the negative 7th meters. So this is a perfectly valid answer, but the problem should have stated what is the wavelength in meters, because we typically describe the wavelength of visible light in meters, or excuse me, in nanometers. So back that up. The problem should have said express your answer in nanometers. So let's go ahead and convert from meters to nanometers. So 5.88 times 10 to the negative 7th meters. I drop the units of meters down here. I put nanometers on top. So I remember back that nanometers corresponds to 10 to the negative 9th power. I put a 1 beside the number with the prefix. I put the number beside the base unit. So go ahead and type that in the calculator and see what you get. Okay, so when you type that in, you should get 588 nanometers. Okay. So not that I would ask you to, but if you were for some reason memorize the wavelength values for visible light, if you saw 588 nanometers, you could automatically tell me what color that is. So that corresponds to a specific color. And that's not the only wavelength that corresponds to that color. There is a range there, but just know that each numerical wavelength only corresponds to a certain color if it falls in that range, or if it falls outside the visible range to a certain type of electromagnetic radiation. So if you go ahead and look at the second problem in the notes, it says determine the frequency of light whose wavelength is 4.257 times 10 to the negative 7th centimeters. Okay, so I start off with wavelength. Oops, I'm sorry, I went too low. Start off with wavelength is equal to 4.257 times 10 to the negative 7th centimeters. So hopefully automatically you recognize, hey, if I use this formula up here, I can't have a wavelength in centimeters. It must be in meters to cancel this out. Obviously, you could convert the speed of light into centimeters, but it's pretty standard to work with the wavelength, not the speed of light there for conversions. So let's go ahead and convert this from centimeters to meters. So I have 4.257 times 10 to the negative 7th centimeters. Centimeters, meters, just so I cancel that out there. Centi corresponds to 10 to the negative 2, and I put a 1 beside the number, or excuse me, 1 beside the prefix, the number goes beside the base unit, so that cancels that. I'm left with meters, so I go ahead and type that in the calculator. Okay, so you should get 4.257 times 10 to the negative 9 meters. Let's go ahead and stop and do a logic check. Okay, so this number is smaller than this number. So should I have fewer meters than I have centimeters? Yes, that should be logical to you, so you know you're on the right track. So now we can look at the formula. The speed of light equals wavelength times frequency. I can go ahead and do simple algebra and solve for frequency here. I can say that frequency is equal to the speed of light divided by wavelength. I can go ahead and plug in here and say frequency equals the speed of light 3.0 times 10 to the 8 meters per second, and yes, I'm going to include my units here, divided by the correct wavelength, the correct units, 4.257 times 10 to the negative 9 meters. Okay, so go ahead and you see that meters cancels meters, so you're left with nothing over seconds. Okay, so that's a 1 over seconds, so that's a hertz, so we're on the right track. So let's type in the calculator and see what we get. Okay, so we should get, and I'm going to read off what I got from my calculator, 7.047216, it keeps going, times 10 to the 16th. So rather than write all that down, let's go back to the original problem and count my significant digits. Decimal is present, so I'll start on the left, 1, 2, 3, 4 significant digits. So the answer I'm going to write down is 7.047 times 10 to the 16th. And a couple of options. I can write hertz, I can write inverse second, I could write waves per second, I could write 1 over second. Okay, so hertz is the standard unit there, but any of those other units are equivalent there. So hopefully you see these calculations aren't terribly difficult. We only have one formula. The exponents can be tricky in the calculator. If you have trouble with that, go ahead and put your numbers in parentheses before you type it in. The one big thing to remember here is to write your units in every single calculation, and that'll help you catch if you don't put them in the correct terms if you forget to convert. So the fact that these calculations hold true, and we can use these calculations to determine the frequency or wavelength of different colors of light or different types of electromagnetic radiation, is just another, I guess you could say, point in favor of the wave theory of light. So we're going to end this video here. In the next video we will look at the particle theory of light.